So the question I ended on, what do I do in this situation? How do I account for the fact that I no longer have distinct roots, but instead have a repeated root? I can't do the same thing. I cannot say, oh, my solution should look like because those are the same damn thing. And it doesn't make any sense for me just to put the thing in there twice. It wouldn't work. What I need to do is establish some sort of difference between the left term and the right term. So in a later course, either in linear algebra or in another higher course, we'll talk about the idea of independence. I want to make these two pieces independent of one another. Currently, they're exactly the same, except for what numbers in front. I don't know what those numbers are yet. So in order to make them independent, I'm going to add something to the second version. I'm going to put an extra n. And by doing that, I create two different pieces out of the same value. I have 2 to the n, and I have n times 2 to the n. And these two pieces are independent of one another. Whenever I have a repeated root, I will do this. And that extra n showing up in there is what makes my solutions independent of one another and allows me to then use the same process of solving for R1 and R2. So let's go back and look at our problem again. With those starting values, and having found that the only root is 2, I know that an should look like this form we have up here. How do I find alpha 1 and alpha 2? I'm sorry? I'm going to use the terms we were given right here. So when n is 0, A0 is 6, but that's also alpha 1 times 2 to the 0 plus alpha 2, wait, times 0 times 2 to the 0. What's that whole term? I solved for alpha 1 right away. Ooh, I like that one. What's alpha 2? I'm sorry. N equals 1. A1 is 8. Let's solve for alpha 2 here. That's alpha 1, 2 to the first, plus alpha 2 times 1 times 2 to the first. So that's 2 alpha 1 plus 2 alpha 2. But I know alpha 1 is 6. So alpha 2 is which means I now know what alpha n is. That's what an is. An is 6 times 2 to the n plus negative 2 times n times 2 to the n. If I factor out the 2 to the n, I get 6 minus 2n instead of parentheses. So because I only have one root for my characteristic polynomial, I end up with a linear equation for a solution as opposed to a strictly exponential equation for a solution. There is one other possibility. When I do a quadratic equation, I could have two distinct real roots, I could have a repeated root, or what's my third option? I could end up with imaginary roots. I could end up with complex numbers. Guess what we're not going to touch in this course? There is a method by which I can do this same process involving imaginary numbers. It requires me to do a lot more stuff in complex numbers in the first place, well beyond the scope of this course. Several identities we have probably not covered at all, unless you just barely saw some of them in complex variables or in your trig course, maybe, depending on your pre-calculus instructor. So we're only going to look at these options. I either get real roots that are different or one real root that is repeated. We'll save complex numbers for something else. Those of you going on to do modeling, recurrence relations are very well and commonly used in this sort of modeling behavior, like looking at infectious diseases. The number of people suffering from this disease depends on how infectious it is and how many people were suffering from it last week. That's exactly a recurrence relation. If there are other factors involved, I can get more complicated recurrence relations. We'll address those more in a differential equations course. All of this was based on the assumption that I had a recurrence of degree 2. What happens when I have a recurrence of degree 3 or 4 or 17? It's going to depend on my roots again. So here's my characteristic equation of degree k. Let's suppose we're back in the first case. All of the roots are distinct. Then instead of having two pieces, I have k of them. But in order for me to do this recurrence, I will then need k different initial conditions. So just like we had a 0 and a 1 back when we were doing degree 2, I would need a 0, a 1, a 2, all the way up to a k minus 1. But that means I'm going to have to do more algebra. This actually makes me happy because I've turned what looked like a really difficult recurrence problem into just solving an algebra problem and then plugging and chugging for simultaneous equations. Let's see if we can figure out this one. We are of degree 3. Because I go from an to an minus 3. So I need a characteristic equation that will be a polynomial of degree 3. What are the coefficients of that polynomial? But I've got r's that go with that, right? What powers of r go with what? But we know k is 3. R cubed, subtract 2, r to the first, subtract 3, r to the 0. The other way you could do it is you say, oh, I'm going to do r to the n is 7 r to the n minus 2 plus 6 r to the n minus 3. And then I'm going to divide everything by r to the n minus 3. Over on the right here, that's no r's. Here, that's going to be 1r. Here, that's going to be 3. Same result. Put it all on one side. I get r cubed minus 7r minus 6 equals 0. Now I have a problem. It's not a huge problem, but it's a small problem. How do I solve that? Algebra class was a long time ago, man. I'm not sure what that'll get me. If I factor out that r, that gives me an r squared minus 7, but I can't set that equal to 0 because it's not a product of things equal to 0, right? And there's nothing factored out of the 6, so I can't take that out either. Oh, I'm close. What else can I do? I'm sorry? I could if I knew. The problem is that I'm not sure that works for a cube. I know that works for a square, but I'm not sure that works for a cube. I know there is a formula for a cubic equation by Tartaglia and Cardano. Girolamo Cardano wrote the cubic formula in the 1500s. You know it? Me neither. That's not going to help. There's something out there that'll do this. I just don't know it. That sounds good to me. Damn. There are some options I can play with. If I think about the foiling idea, I say to myself, well, really what I would want is two numbers that when I multiply them together, I get -6. But I add them, I get -7. I'm not sure that works. Oh, wait, no, this is a cube. I'm not sure that's going to work anyway because it would not multiply in the right fashion. Oh. I could guess and check till the cows come. But I have a computer that is unconnected to the internet available to me. This is, I'm solving an equation, right? Graph the damn thing. X to the third minus 7x minus 6. Graph it. Oop, I have a really crappy window. Let me fix that. Zoom, standard window. 1, 2, aha, there are 3 x-intercepts. Those 3 x-intercepts, those are the 3 values that work. I have 3 distinct roots. What are they? Second, calculate where my value is 0. So I can have it do it for me. I say, oh, well, that value over here on the right, that looks like it's around 3. So let's get, say, -2 on the left, bigger than 3 on the right, and then give it a guess, and it says, oh, that happens to be exactly a 3. The y value is 0 when x is equal to 3. Perfect. I can do the same thing here and the same thing here, and lo and behold, it's -1 and -2. So it turns out I can do this without ever having to know that weird cubic formula. If I did find one of the roots, I could do polynomial division and the rational root theorem and the factor theorems that I learned about in my algebra class. How many years ago was that? Draw the picture. A lot easier. Okay. How do I get from here to the finish line? What does my solution look like now that I know my roots? My solution looks like that form right there. AN equals. Now it's going to be up to you, depending on what order you put these in, as to what number you get for alpha 1, for alpha 2, and for alpha 3. How do I find the alpha values? Say again. So back up here, the initial values I have are A0, A1, and A2. A0 equals 9. What do I get for an equation out of that? I put in all of those n's as zeros. What happens here and here and here? They just turn into ones. -1 to the 0, -2 to the 0, and 3 to the 0. So I get alpha 1 plus alpha 2 plus alpha 3 is equal to 9. A1 was equal to 10. So what goes on the left side of the equation equal to 10? And then I did alpha, I'm sorry, A2 was 32. So something is equal to 32. What's the something here? What's the left half of this equation? Ian? Because it's -1 squared, -2 squared, and 3 squared, 1, 4, and 9. I go all the way back to my algebra class again. You have to solve 3 equations in 3 variables. How do I do it? That would be the method of substitution, right? I could take that first equation and say alpha 1 is equal to 9 minus alpha 2 minus alpha 3. Put that into the next 2 equations. Those get converted to just having alpha 2 and alpha 3. That works perfect. I then solve those 2 equations in the 2 variables using the methods we did on Wednesday. Cascade, what's perfect? Not exactly the short method. What else could I do? The method of elimination by addition still works for 3 variables. So I could take 2 of them and eliminate one of the variables, say in 1 and 2. Then I could take 1 and 3, and I'd end up with 2 equations in 2 variables. Alpha 1 plus alpha 2 plus alpha 3 equals 9, minus alpha 1 minus 2 alpha 2 plus 3 alpha 3 equals 10. If I add those, the alpha 1s cancel out, right? Minus alpha 2 plus 4 alpha 3 equals 19. Similarly, if I take the first equation and the third equation, alpha 1 plus alpha 2 plus alpha 3 equals 9, I'm going to take that third equation and make it negative. Negative alpha 1 minus 4 alpha 2 minus 9 alpha 3 equals negative 32. The alpha 1s will cancel out again, won't they? Now I have 2 equations and 2 variables, don't I? Notice, by the way, this is the same set of equations I would have gotten if I'd done what you suggested, Emily. If I take alpha 1, made it 9 minus alpha 2 minus alpha 3, and then plugged into the second equation and the third equation, I get exactly these. But 2 equations and 2 variables, I know how to deal with that. Okay, so I'm going to take this equation and multiply it by 2. Minus 2 alpha 2 plus 8 alpha 3 equals 38. Over here, I have minus 3 alpha 2 minus 8 alpha 3 equals negative 23. What happens when I add those? So I end up with minus 5 alpha 2 equals 15, or alpha 2 equals 3. Now I can go back and solve for alpha 3 by putting this into either one of those equations up there. Minus 3 plus 4 alpha 3 equals 19. That means that 4 alpha 3 is equal to oh, wait a minute. Nope. I made a mistake. Where's the mistake?
5, 14 by 6, 38.
That's a 19. But my mistake is here. I divide by negative 5, which makes that a plus. Helps if I don't make a sign error, minus 1 to me. So 4 alpha is 16, alpha 3 is 4. And now I can go back. Alpha 1 plus alpha 2 plus alpha 3 equals 9. Alpha 1 plus 1 equals 9. Alpha 1 equals 8. So AN is 8 times negative 1 to the n minus 3 times negative 2 to the n plus 4 times 3 to the n. Still not very fast, is it? How many of you have ever studied matrices? Or understand that the matrix has nothing to do with counter roots? There's a way to do this in one step. I'm going to go back and look at the 3 equations I started with. The 3 equations I started with. Alpha 1 plus alpha 2 plus alpha 3 equals 9. Minus alpha 1 minus 2 alpha 2 plus 3 alpha 3 equals 10. And then alpha 1 plus 4 alpha 2 plus 9 alpha 3 equals 32. The alphas themselves could be any letter at all. I could use X, Y, and Z. I could use Fred, George, and Harry. It doesn't matter what symbols I have. What matters is the numbers that are in front of them. I'm going to take only the numbers. Subtraction means that number is negative. I'm going to write down an array with just the numbers. That vertical bar that I've drawn there, that's force of habit. That's where the equal signs were. You don't need it. It's not required. Helps me to remember, though, that that's where the equal signs work. This has 3 rows and 4 columns. This is a 3 by 4 matrix. Rows, columns. I find it easy to remember RC. After all, Seton Hill is a Roman Catholic institution. So, please notice, on my graphing calculator, there's a button that says matrix. Right there. Matrix. Please find me a white balance again. There. I hit that button, and it gives me a list of matrix options. I want to edit a matrix. So I'm going to go to edit, and I'm going to edit this first matrix. The first thing it asks me is, how big is it? Matrix that's in there that I used last was 4 by 4. But I want a matrix that's 3 by 4. And now I just have to type the numbers in. And every time I hit enter, it's going to go across the row. When I reach the end of a row, it's automatically going to wrap back around. See these little dots here? That's what tells me there's a 4th corner across the edge. So 1, 1, 1, 9. That's the first row. See the end of the matrix? Second row, -1, -2, 3, 10. Last row, 1, 4, 9, 32. Here's my matrix. I'm going to quit out of here. Second, and the mode button, it says quit. I can go check. Matrix. Promise I'll hit the right button eventually. Matrix A is now 3 by 4. I say, hey, what's in matrix A? Is that the right entries? Right numbers in the right places? Good. The way to get the answer out is to put this matrix in what is called reduced row echelon form. RREF. So I'm going to go back to that matrix menu. And that first column is where I just have the list of all the matrices. Middle column says math. The middle column is where I can do things to a matrix. I can do all sorts of crap to a matrix. See that little arrow at the bottom next to the 7? Means there's more stuff going down. So let's go down. Hey. What's option B? Reduced row echelon form. I want to do the reduced row echelon form of what? Of matrix A. So let me go second, matrix, put in matrix A. I just need the name, hit enter. I want to do the reduced echelon form of this matrix. Bang. What does that say? Just like these are equations, this is a set of equations. Let me copy it down. Now, the calculator, unfortunately, is stupid and doesn't know that there's supposed to be a marker for the equal sign. So I'm going to put that marker back in. These came from these equations. So the first column represents the alpha ones. And the second column represents the alpha 2. And the third column represents the alpha 3. So what's the first row of this matrix as an equation? That's alpha 1. The middle equation is 1 alpha 2 is equal to -3, and the bottom one is 1 alpha 3 is equal to 4. Isn't that what I got by doing all the work by hand the long way? I don't have to do that. I don't have to do that. Just like I didn't have to know the formula for solving a cubic equation, I could graph it and take the intercepts off the picture. I can do the same thing. All I have to be able to do is let the code for solving a matrix do the work. Questions? Talk to me. Problem was rigged. It was a special case. What was special in the sentence I set up at the beginning was I said that I was going to assume, again, that we had distinct real roots. It is possible in an equation of higher degree that we can have all sorts of repeated options. I could have a one root repeated twice and another one that was different. Or I could have all 3 roots be the same. If I had 6 roots, I could have one that was repeated twice, one that was repeated 3 times, and one that was only repeated once. Crap, how do I deal with multiple roots? Every time I have another copy of the same root, I add an n. If I have one root 2 times, I have that root, and then I have n times that root. If that root shows up 3 times, I have 1 and n squared. If that root shows up 5 times, I have 1 and n squared and n cubed and n to the 4th. A multiplicity is the number of times my root repeats. If the root only shows up once, then the multiplicity is 1. If it shows up 3 times, the multiplicity is 3. Shows up twice, the multiplicity is 2. Shows up 7 times, I've got multiplicity 7. And that's all the roots. I'm not missing anything. No complex numbers here, no imaginary anything. These are all the roots. Then What the frack? All right, I didn't give myself enough room. Let's write that more clearly. Alpha 1, comma, M1 minus 1, N to the M1 minus 1 power. What the hell? Oh, the M1, that's the multiplicity of the first root. I need a 1, an N squared, all the way up to 1 less than that multiplicity. And I'm going to have a 1 coefficient for each of those. And then I do the same thing for R2. Alpha 2, 0, plus alpha 2, 1, N, plus dot, 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 plus alpha 2, M2 minus 1, N to the M2 minus 1. Plus dot, 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 all the way to RT to the N. Alpha T 0, alpha T1, N. Alpha T, comma, MT minus 1, N to the MT minus 1 power. Holy crap, that's disgusting, isn't it? No. These are just double subscripts because this is the first root's 0th power event. This is the first root first power event. This is the first root M minus 1, M sub 1 minus 1 power event. It's just keeping track of where I am along that list. It's a double subscript simply so I can keep track of which number is which. Just like I had alpha 1, alpha 2, and alpha 3. I'm going to have K of them, but I'm going to group them by which root they go with. Yes, absolutely disgustingly gross. I'm 100% in agreement with you. I hate this formula. So how do I remember what the hell I'm doing? I remember it by every time a root repeats, I need another N. Suppose, here's an example. I'm not even going to write what the first 3 values are. I only want to set it up. So I'm writing R to the N equals 3R to the N minus 1 minus 3R to the N minus 2 plus R to the N minus 3. I divide everything by R to the N minus 3, and I get R cubed equals 3R squared minus 3R plus 1. I move all that over, R cubed minus 3R squared plus 3R minus 1. I cheated. I rigged this really substantially. This is R minus 1 to the 3rd power. I worked it out ahead of time, which means the only root is 1. And it's got multiplicity 3. If it's got multiplicity 3, it shows up 3 times, right? So I'm going to have AN is something times 3 to the n plus something times 3 to the n again. No, I need an n because it's there an extra time. Plus something else times 3 to the n. I need another n because it's there a 3rd time. If I were to factor that 3 to the n out, I called this alpha 1, 0. I called this alpha 1, 1. And alpha 1, 2. The multiplicity minus 1. Emily, does that make it better? Every time it repeats, I need another n. It repeated 3 times. I got no ends, 1 end, 2 ends. No. Did it make sense last time when I said I'm repeating it? I have to have something to make it different. I need something to make these 2 pieces different. That's the end. I need something to make this piece different from both of those. That's another end. Every time I need another piece, and it's got to be different, I add another end to the power. Nasty, 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 nasty. So how often do you think I'm going to make you do prep like this? If you're lucky. On the homework, maybe. Why am I going to do this? As I said earlier, modeling situations using recurrences come up a lot, especially in things that depend on time. When I think of time as a continuous idea, I get models like exponential growth, like you saw in Calc 1, where we did our doubling time idea, and we looked at derivatives of exponential equations. 2 to the x, 3 to the x, e to the x. But if I look at discrete ideas, the course is called discrete math, right? Then I'm looking at the number of cases per day, the number of population added each day, each week, each year, whatever. My steps are distinct. A recurrence is more useful. But the idea is the same, even if I'm doing continuous or discrete modeling. Questions? I can take the same idea and add the idea that we had in the Tower of Hanoi problem. What was the difference between what we were doing today and Wednesday and what we did in that Tower of Hanoi? On Wednesday, I mentioned this in specific. It was a word we used. Number of moves to move 2 n coins was, what was the recursion for that? Technically, we wrote that down a week ago because we did that on the lecture before the exam. So go back and look in your notes. And that +1 made this different. What kind of an equation is this? This is no longer homogeneous. Because that piece doesn't depend on another term. It's just a +1 every damn time. Well, I could be looking at recurrence relations that have lots of non-homogeneous pieces. It turns out, in order to solve the one that's not homogeneous, the first thing you do is solve the one that is homogeneous. So all the techniques we just did yesterday, Wednesday and today, are the things we need to be able to solve higher models. It's how we deal with that +1 that depends on the type of solution we get and what this looks like. The recurrence in the exam, we had an n as a coefficient, right? That didn't have constant coefficient. I would need a different technique. Dealing with non-homogeneous equations, there are several different methods for solving these, most of which I think are beyond the scope of what I'm going to cover here. In code, it's almost always easier to let it write the recurrence. But only when I'm doing short to moderate length projection. If I want to go out to 100 or 1,000 or 10,000, I'm probably going to want the closed form instead. Simply for ease of computation. So, There's an entire discussion on how to address non-homogeneous terms in the textbook. If you find yourself suddenly at some point in the future going, shit, I need to know how to solve this. Let me go back and remember that it's not homogeneous. All right, what the hell do I do? That's what the textbook is good for, as a reference. I will not ask you in this course to solve non-homogeneous equations. Applications of recurrence relations are in every field. Every. And the uses we have and the ways in which we find patterns in recurrences span lots of different options. More to come in other classes, but not here. On Monday, I'm going to look at, again, another trip back to theory side. I'm going to go back to functions and sequences and stuff that we did back in chapter 2. So for Monday, in addition to turning in the homework for 8.1, please go back and reread chapter 2, section 4 on functions. Sorry, chapter 2, section 3. 4 was on sequences and series. Read the functions section again. We're going to use it on Monday. I will see you all then. Have a wonderful weekend. If you came late, I have stuff for you. Come get it.